Good day, grade 12s. I'm T Sonnekus. As part of the STEM in Action Boost series, I'm going to demonstrate a titration for you. So as with all experiments, we need to start with an aim. Okay, so the aim of this titration is to determine the unknown concentration of oxalic acid by titrating against a standard solution of sodium hydroxide. So there's the basic formula for the reaction, and as you can see, we want to determine the concentration of oxalic acid, and we know what the concentration of sodium hydroxide is. So the definition for titration is as follows: the method used to determine the concentration of an unknown substance using another standard solution. So titration is also a neutralization reaction between an acid and a base. In a titration, a known volume of standard solution A is added to a known volume of solution of an unknown concentration until the endpoint is reached. So now you want to know what is a standard solution. A standard solution contains a known or an accurate amount of a substance or an element. In this case, our substance is sodium hydroxide. So we measured it, I accurately measured on a balance, so I know exactly how much sodium hydroxide I added to a known liquid or known volume. And so I know exactly what that concentration is. For the endpoint is where you will observe a color change from the indicator. Okay, so we have different indicators, okay? And something you need to be able to do in grade 12 is to motivate the use of an indicator. So basically we have three main groups of indicators: methyl orange, phenolphthalein, and bromothionyl blue. And as you can see, a methyl orange we use with a strong acid and a weak base, so that combination. Phenolphthalein we use a weak acid and a strong base, and bromothionyl blue for a strong acid and a strong base. Please remember, the strong and the weak doesn't indicate the concentration, but what type of acid that is. Okay, then let's start with the titration. I'm just going to quickly introduce you all the materials that we're going to use. Okay, and we're going to start with this retort stand. We've got a retort base and we've got a buret clamp onto the retort stand, and inside the buret clamp we've got a buret, a 50 milliliter buret. Okay, so it's graduated in 1 milliliter increments, and we can measure accurately 50 milliliters of using the buret. Then I've got a buret funnel, because this is quite a small opening there in the top, so I've got a buret funnel for that. We've got a 25 millimeter pipette. I've got a pipette pump as well. I've got a white paper to indicate more color change for me. Then I've got a conical flask. I've got a couple of glass beakers here for use. I've got a Pasteur pipette, and then I've got my standard solution of sodium hydroxide, and I've got my unknown concentration of oxalic acid. Then lastly, I've got phenolphthalein, and the phenolphthalein is going to be my indicator. So that was the materials for everything that we need for this experiment. So let's go on to the method. So we're going to start off taking my sodium hydroxide, and we're going to fill the buret with sodium hydroxide. For that I need my buret funnel. I need a beaker just to pour this into there. So I'm going to just add about 50 mils or so in there. And I'm just going to clamp this out because I feel it very awkward, even though I'm told to work at over here, and it's not a good practice. It's trying to work somewhere in the air, so you must just make it comfortable for yourself. Something with a buret, please remember always to check whether the tap is closed. Okay, when you see, if you look at this, you'll see that it forms a cross. When it's a cross, it's closed, and when it's in a straight line, it's open. So it's just to make sure it's closed and forms the cross. Then you're going to take a little bit of sodium hydroxide, my standard solution, and I'm just going to add a couple of milliliters inside there. Just going to put this down again. I'm going to take this. I'm just going to give it a quick rinse, just to make sure that everything inside there is what we want and there's no residue from a previous experiment. And I'm just going to empty it into my waste beaker over here. Okay, nice and clean. And then I'm going to fill it up with sodium hydroxide. Just going to pour it in there. Okay. Okay, I'll overfold it a little bit, but you'll see just why I've overfolded. I'm just going to put it quickly back into its clamp. Just move this up a little bit and make sure everything is nice and tight. I'm going to take this out, move it to the side, and something that we just need to do is to remember to label my equipment. So this is NaOH. I'm going to just leave it onto the side, and this is going to be the waste beaker. I've overfolded with about 2 milliliters. So what I'm just going to do, I'm just going to open the cap slightly, and I'm just going to get my meniscus down to onto the 0 value, and almost there. There we go. So you will see the meniscus. We all know meniscus is that curvature of the liquid, and you want that bottom part of the meniscus just to touch the 0. Okay, now my buret is all set up and ready to use. So now my buret is all filled up, and the next step is to pipette 25 milliliters of my unknown concentration of oxalic acid. So let's do that quickly. Grab the oxalic acid, a small glass beaker, and we're going to grab the 25 ml pipette. So once again, I selected the equipment that's needed to do the specific job. You can use a measuring cylinder. You do not need to use a posterior pipette, but I just find it convenient because it's already graduated. I know it's 25 milliliters, so it's much easier to use. I'm just going to put it down quickly there. Take this, pour it out. Now I've got my oxalic acid, and what did I forget to do? I forgot to label my beaker. Okay, so we just need to do that. And then do the full name, just OA, oxalic acid. Okay, let's put this away again, and grab the pipette. So put this in there, and suck it up. Wait a little bit, goes quite fast, then it slows down for the big bulb. That's why it's called a bulb pipette, due to this. Just go slowly, we get to our line for 25 milliliters. I take this out, and I can pipette it into the conical flask. Something about the pipette is, you'll see there's always in the tip, there's like a little bit that's left behind. So if you actually shake that little bit out, you're actually adding way more than 25 milliliters. So there's something that you don't need to do, is you don't need to shake that little bit out, because it's already been graduated to take that into consideration. Okay, so you can just take this off. You don't need that anymore. Just make sure there's no drops staying behind, and you can take this and move it away. We finish with that. Okay, now we know we've got accurately 25 milliliters of oxalic acid, or unknown solution in here, and we need to add our indicator, because if I add sodium hydroxide into here, we're not going to see a color change happening now. So we need to add something in there. And we know that sodium hydroxide is a strong base and oxalic acid is a weak acid. So my indicator choice is phenolphthalein. The moment you'll see phenolphthalein, it's a clear liquid. When we add it to an acid, it's still going to stay clear. Because in an acid environment, it's a clear liquid. When I put it into I can actually show you that. Let me demonstrate it. So I've got a little bit left over here. Let's take the phenolphthalein and we just add a couple of drops in there. You see, they don't even have to do a lot of drops. And you will see that the base will change to a color. Okay, so that's the color that will be when it's in. So you just add 1, 2 drops. That's the only thing what we need. And you just can move that to the side. So then we know that we've got our oxalic acid and our indicator in here. Okay, so we can take the waste beaker away and we can put in our LMR or conical flask in there with our unknown solution. Now everything is set up and we can go ahead and do the titration. So I'm just going to go down here. I'm going to open my tap and just going to start running it down. As you do this, you can see this where the sodium hydroxide is hitting the indicator. It's showing a slight pink color in there. Let's slow down slightly and let's not go too fast because the pink is staying slightly longer around. So with this pink color, you'll see that the pink color stayed and then it sort of disappeared again. If it stays there for like a second or 2 seconds and disappear, I will stop my titration just there, because that will show me that it's on that edge of at the end point. Because that color change. If it stays too long, then we slightly over titrate, and so we're on the edge for that. Okay, I'll show you now when we add 1 more drop or 2 more drops to this, what's going to happen to that color change in there. But first, what I want to do quickly, I want to record all my values that I need for my calculation. We started with the buret. And we remember that initial volume when we started that was set at 0. So that was my initial reading. My final reading, it's sitting at 24.9 milliliters. So that's 24.9 milliliters. And so the volume that we titrated is the difference between that. So we know we titrated 24.9 milliliters. Okay. Oxalic acid, how much oxalic acid did we use? We used 25 milliliters, so you can just fill that in as well. And then we can go back to so the concentration of a standard solution, we know that is going to be 0.2 molars. Okay, so we just remember all the values that we used for that. So basically now my titration is complete. Okay, I can take my values that I've got, I can go plug it into my equation, and we can go and calculate the concentration of the oxalic acid. Okay, but let me show you the pink color. So when we go a little bit more and we add a couple more drops in there and we shake it, we'll see that the color is changing. And that will show me that I've over titrated. And that's not the color that I'm looking for. I was looking for that faint pink color that lingers a little bit and then disappear. Then we know that is our end point. Okay, as you can see, this color is going to stay there for a while. Okay, and ladies and gents, let's see how we can do the calculation. So first thing we need to do is we need to take our equation and we need to balance it. Okay, so if we look at this, you will see that there is, let's start with the sodium hydroxides, or the sodiums. You will see that there is on the left hand side, there's 1 sodium, and on the right hand side there is 2 sodiums. So we need to know we need to add 2 more sodiums in there. So we say there's 2 sodiums on the left, and then now there's 2 sodiums on the right. Okay, then we can look at the carbons. You can see there's 2 carbons on the left hand side and there's 2 carbons on the right hand side, so that's all good. The oxygens, You see there's 4, 5, 6 on the left hand side now, and there is going to be 4, 5 on the right hand side. So we need to add another oxygen. So now we've got 6 on the left and 6 on the right hand side. Then let's see quickly hydrogens. We've got 2 hydrogens, 4 hydrogens on the left hand side, and 2 times 2 gives me 4. So that's 4 hydrogens on the left hand side. So now I know my equation is balance. So from our balance equation, we can see that there's the ratio of oxalic acid to sodium hydroxide is 1 to 2. Then step 2 is we record all our data, and for our something important that we must remember is to convert my milliliters to decimeter cube. As moles per decimeter cube is the final answer we are looking for our concentration. So we need to do that. Okay, so remember, convert from milliliters to decimeter cube. How do we do that? We divide it by 1,000. So then we move on to step 3, and we calculate the number of moles of sodium hydroxide that are needed. And we use the equation N equals C over V, and N equals 0,2 times 0,0249, and that gives me 0,00498 moles. Then we move on to step 4. We calculate the number of moles of oxalic acid. Remember, we need to balance the equation, and we know that we need to halve that number of moles. And we say N equals half times 0,00498, and that gives me 0,00249 moles. We take that answer, we plug it into this equation for step 5. We calculate the concentration of the oxalic acid, solution, and we see that the concentration is going to be 0,00249. We divide it by the volume of the oxalic acid, which is 0,025, and we get a final concentration of 0,0996 moles per decimeter cube. Okay. Then we can say the concentration of the unknown oxalic acid solution was 0,0996 moles. So therefore we can see that the concentration of the unknown oxalic acid solution was 0,0996 molar. And the capital M is the same as moles per decimeter cube. And ladies and gents, with that, I hope that you see that titrations are not that difficult. It's quite a fun experiment to do, and just going through those steps, break it down into bite-sized pieces, and you'll see that it's quite easy to calculate your unknown concentration of that. And always remember, your standard solution are going to be in a buret, and my unknown solution is going to be in my conical flask. And ladies and gents, that brings me to the end of the Boost Titration series.